Okay, this video is going to show you how to set up a simulation of a YouTube heat exchanger. It's a very simple device. It's a tube here that is bent into a U shape. Fluid goes in one end, comes round and out the other, and along this path it exchanges heat across the wall of the tube. And this is a diagram of a YouTube heat exchanger in the ground. This stippling here is cement, and this is the ground here. These are some people that are installing a YouTube heat exchanger in a borehole. There are the two tubes. You put it in the hole, it goes in here, the tubing is unwrapped, goes down to the bottom, fill it up with grout. And this is a picture of a building, perhaps a school or hospital, where there are multiple YouTube heat exchangers in the ground. Water is circulated through these, and it's used to either cool or heat the water. That then cools or heats the building. Many new construction of buildings like this, schools or hospitals, have these kind of heat exchangers. Some houses have them as well. This general geometry can be used for a variety of other applications, and here's a bundle of many U-tubes that are put together for an industrial application. Fluid is put in here, circulated through these tubes, and then this whole bundle is put into a chamber that has liquid or gas circulated through it to exchange the heat. So fairly versatile kind of geometry and fairly effective at exchanging heat. So let's set up a simulation that allows us to analyze this. So here's the model, and it's been run. The YouTube you can see is right here. The overall geometry is this cylindrical domain, and this slice shows the temperature distribution. So we've got some pretty significant temperature change around this tube and much less around this tube. So the hotter water is going in here, circulating and coming out. Cooler there. And if we zoom out, we can see underneath that there's a little bit of temperature change, but if I bring this slice up here right at the bottom, you can see that, yeah, it's effective over the whole length. So the trick to setting up this model is to get this YouTube geometry entered correctly, and then to set up a mesh that will give you the right answer for the flow and the heat along this temperature along this tube. So let me show you how to go about doing that. Here's the overall geometry. It's this cylindrical region, and you can see the tubes are right there. And so the tricky part here is to get these tubes so that they can be get the tubes entered right. So I'm going to go and view the unhidden geometries, and there you can see the YouTube. So the YouTube is made of three entities. Two of them are just cylinders. And so if I here are the cylinders specified by radius and height, and if I build them, I get these two guys right here. They're the same. It's a 1 centimeter radius and a 1 meter height, and one cylinder is at the origin here, and then one cylinder is offset by 0.1 meters. And so the trick then is to get this connection between these two cylinders. And the way that I did it was to put in a work plane, and you can see the work plane has appeared down at the bottom of the cylinders there. And so we can move the work plane around. If we wanted to move it up, we could do that. But in this case, well, let me take a look. Let me show you what it looks like with the work plane at that location. So here it is. These are the intersections of the two tubes, this one and this one, and I've drawn a circle right here at this location. So I did that by just inserting a circle in the geometry like that. And then I'm going to, that's it for the work plane. Then I'm going to change that into this curving tube with a command called revolve. And so I'm first going to drop the z coordinate down to there. So the work plane is back at z of 0, and I've still got this circle in, and I'm going to put in this revolve command, and that's done selected here from geometry. It's right there. So if you put that in, here are the specifications, and what's going to happen is we're going to take the entity that we've drawn here in the work plane, and we're going to revolve it around this axis, and we're going to do it by a certain angle. So we're going to revolve it. It's going to go from here. It's going to revolve by 180 degrees around like that. Okay, so there's the magnitude of the angle of the revolving, and it's 180 because it's in a counterclockwise direction. And this axis of rotation is specified by giving it a location, x of 0.05, which the axis is in that direction, and y of 0. So this is in the work plane, and so it's right there. And then the direction of revolution, you can think of this as a unit of 0 along the x-axis and a unit, say a unit vector of length 1 along the y-axis. If I were to change this to 1, then it's unit length of 1 along the x and y-axis, which is 45 degrees. So those are the important specifications, and if I build it, I see that it wraps around like that. If I change the axis of revolution like that, then I get a different geometry. It is wrapping then around this geometry, around this axis like so. Okay. So there's a great deal of flexibility here, and we can get really a wide range of geometries. So that's how you get this U-tube geometry. And then we also want to add to it this outer cylinder that will be the overall computational domain. Okay, so that's a U-tube. We can make it longer, we can make it wider, we could copy it, we could do a variety of things once we've built this main entity. Okay, so that's one trick. I'll show you how to set up the physics in a second, but let's go here to the mesh, because this is going to be a little bit of a trick. If we go and use the default mesh, then here's what the default mesh looks like. We get quite a fine mesh here in the tubes, and if we zoom in on the top of the tubes, we see that there are several entities or several elements here with distance, and also I think there may be even more elements along the circumference. There are settings for the mesh resolution, and I think I might not really be seeing all of them. In any case, if we look down here at the number of elements, 136,000 elements, it's certainly possible to solve this, but it'll be a fairly large mesh for solving on a PC. Actually, I mean, it's not that big of a deal, but we can get a mesh that works satisfactorily that's much smaller. So let me show you how to do that. Um, Instead of just meshing the thing with a default mesh that's quadrilateral everywhere, we're going to mesh it with a uh, quad mesh. Um, just a sec. Yeah, with I'm sorry, not a quadrilateral, but the default is a tetrahedron. So instead of having a tetrahedron everywhere, what we're going to do is mesh the tube separately, and we'll put a quad mesh on this end of it. So there's the mesh, and the it's going to be eight-sided, and so it's not really showing you all of the elements. So it'll be this quad, and then we're going to sweep it along the tube. So for this swept mesh, we end up with something that looks like this. Okay, let me hide these as well, these faces. So there's that mesh, and then the next one. What I'm doing here is I'm creating three swept meshes. The first one, I took the I took the mesh that I made on this face, and then I selected this subdomain, it's subdomain 4, and I used the top face as the source face and the bottom face as the destination face down there. You can see it here just a second. Okay, so there's the destination face, and then I give it a distribution. This allows me to specify how many points there are along this mesh, and I specify 25, and then we go ahead and mesh it. The next one, I do the same thing for this element. I specify the subdomain, the starting face, the ending face, and the number of points. If I build that, I get a mesh that looks like this. And then I do the same thing for the next mesh. Identify the subdomain, the starting face, the destination face, and here I've got the number of points. So I build that. Okay. So now I have these square-sided faces, and that's what you get when you use a swept mesh, because it takes the mesh on this face and it sweeps it as a quadrilateral. I guess. Anyway, what you get is a rectangle on this face. Now, when I'm going to go and finish out the rest of the mesh here, I'm going to use a tetrahedral mesh. The tetrahedral mesh will have triangular faces, and here we see a rectangular face. And so if I try to do this, I just tried to do this, I'm going to get an error. So I failed to generate it. The boundary mesh must consist of triangular elements only. So when you have a tetrahedral mesh, you can only have boundary elements that are triangular. This swept mesh creates boundary elements that are rectangular or four-sided polygon. So what you need to do is have this command that's called convert, and that converts four-sided to three-sided. And you can see what it does here. It just draws a line from one corner to the other on these four-sided elements. converting them into three-sided elements. Okay, so now it should work here if we build this. So now we have the mesh and we can go ahead and use it. So this mesh is 24,000 elements compared to 136,000, so it's quite a bit smaller, quite a bit fewer number of elements, and so it'll run faster. Now I made up another mesh, and you can see here I've got three meshes in this problem: the default mesh, the mesh where the flow is okay, and the mesh where the flow is a problem. The mesh where the flow is a problem, it differs from the quadrilateral mesh just in a small point. Here the let's see. So this is the starting point. I'm going to mesh this face and then sweep it along through the through this tube. And in this case, the maximum element size is 0.02. And so when I do that, I get a geometry that looks like that. Seem to have lost track of it. Okay, and then I sweep it through, and we end up with a mesh that looks like this, and the rest of the mesh is hidden. By contrast, when I use the mesh with the, it's called mesh flow OK, I've made a bit of a change. The maximum element size is 0.01, half the size of this one. Then when I mesh that, I get this mesh that has a little more resolution in here. Okay, so just a fairly subtle difference. Making that change causes a further reduction in the mesh size, 14,000. So of our three meshes, we have the default mesh with 136,000, the mesh that's called mesh flow OK with 24,000, and the mesh flow problem is 14,000. And so what I'll show you is that this mesh takes a really long time to run, but ultimately it gives you results that are okay. This mesh runs much faster and the results are okay. This mesh runs even faster, but there are problems with the results that really make this mesh unusable. So we'll try all three of these meshes and we can switch back and forth between them. But first let's see how this model is set up with the physics. So we've got laminar flow and heat transfer in fluids. And so I set up the laminar flow first and just added this physics interface and set it up for water. In this case, I just entered the properties of water manually. And in many respects, it's quite similar to what we've done before. We've got an inlet boundary condition that is specified here. Well, let me go, and I'm having trouble selecting these. So let's view all. And reset the hiding. Come on. Okay, so if we zoom in here, this is the boundary that's the inlet at this velocity that's in the definitions. So boundary 10 is the inlet, and you can see we've got this step 1 to ramp up the velocity at the beginning, and outlet is 24. And this is something that we haven't used before, but I have a boundary condition that's called interior wall, and that's going to be, unhide this or hide this. That's going to be the tubes. And what I did was to go up here and I set up a selection in the definitions. I set up a selection and I renamed it tube wall. And here I selected all of the surfaces that are the walls of this tube. And so down here I have an interior wall boundary condition that I got right there. And that allows me to select this as a wall internally. And so the thing that I can do then is have this whole entity be used in the laminar flow interface, but flow is only occurring through this tube here. And that's going to be necessary because under the heat transfer in fluids, I'm going to want to give it the velocities everywhere. And so I have to have all the subdomains active in this region, but I only want the flow going through these tubes. Okay, so interior wall, that's the key thing to getting this geometry or this simulation to work. Under heat transfer in fluids, you should check the heat transfer in porous media and select all the subdomains. And then temperature, this is the input, so we're going to have the temperature specified there and we'll call it Tn. The outflow is boundary number 24. And then the porous matrix is subdomain 1. And that's this subdomain here, everything is not including these tubes. And so under porous matrix, what I'm doing here is giving the properties of the solid material. The solid material, the porous material is 90% porous material, so at 10% porosity. And these are the properties of the solid material: the thermal conductivity, the density, and the specific heat of this is a rock material. I think these values are typical for quartz. Okay, so that's the setup, and I think that's the main things that we need to see. I guess up here we saw the selection, the step to turn on the velocity gradually with time, and then variables, just some simple variables: the temperature in, the velocity in, the initial temperature, these are in degrees Kelvin, and the heat capacity and the density of the water. Okay, so we run it in two steps. First of all, a stationary step, and we'll do that first and take a look at the results. So I'm just running the laminar flow here, and I'm going to try these different meshes. So let's go and do, first of all, mesh flow OK. And if I use that mesh and run this, then it runs pretty quick, and I can take a look at the results here in just a second. Okay, so there's what we get. This is a plot of the velocity along this cross section, and if we zoom in, we can see that we have this velocity distribution that is, I think, what we would expect: high velocity in the center, lower out at the edges. Okay, so this will give us the kind of behavior that we're expecting to get, but let's see what happens if we make this mesh a little bit coarser, and instead of using this one mesh flow OK, we go here. This is under stationary, mesh selection, and we go here to mesh flow is a problem. And if we use that mesh and recompute it, then it's a small mesh, so it runs pretty quickly. But here's what you get. So this is the contour of or a cross section of the velocity, and you can see there's high velocity here, but the velocity here is 0. And so I'm not really sure why this is. You can see they're all like that. But I'm not sure why this is, but it's a problem because it really is working as if the velocity here is 0. And so if you use this for flow or for the transport, you don't really get any heat circulating here by convection. So this is an example of a case where the mesh is really too coarse to calculate a result that is meaningful. It calculates the result, it does it quickly, but there are problems with the accuracy and severe problems with what you would then interpret from this solution. So what I would recommend is that you also go here and try the other mesh, the one with the mesh default. It takes about 3 minutes to run, so I'm not going to do it now. We'll move on. But it's good to take a look and see that mesh, try it out. It's a good example, I think, of a case where the default mesh, it works, and perhaps that runtime is tolerable, but it's a good example of a case where the default mesh can be improved upon quite a bit by being a little bit creative in how you set the mesh up. Okay, so here's the solution with the swept mesh, and this is then stationary flow, the steady state flow, and we'll go here to the transient solver, and this is gonna include let me see, the mesh that's the flow is okay, the physics is just heat transfer, no laminar flow in this case, but in order to do that we've got to use the values of variables not solved for. In this case that's the flow, and so we have to tell it that we want to use the stationary solution for the flow. And I'm also going to watch the temperature here during the solution. So we got it set up, and actually it runs pretty quickly. So there's the result. We're zoomed in pretty close. This is the temperature, and the flow is coming down this one and coming back up here. So the heat is really shed out of the first one in a big way, and coming up it's a lot cooler. And here's the result that we get. So there's the temperature along this cross section, and I think you have an interesting effect where what might happen is that the fluid goes down here and sheds the heat out into the formation, and then coming back up, I don't know, it looks like what could happen is the fluid could actually heat up as it comes back up here, because right here most of this is going to be the hottest point, and so as this heat conducts over here, I think that's what would happen if we were to actually look at the temperature along this profile. The fluid might actually be picking up heat on its return leg, which of course you don't want it to do. You want it to put the heat into the ground, or the other way. So there's a bit of an inefficiency in this particular design. And one of the things we could do with an analysis like this would be to try to find some design variations that were more efficient. Okay, so we saw a temperature horizontal slice before. at the beginning. Another way to visualize this result is with these isothermal surfaces. These are basically contours in 3D, and so that's what the surface looks like, or that's what the isotherms look like. Um, the the reason we're doing this is to put heat into the ground, and heat is energy, and the rate at which the energy is going into the ground is a power, because it's a rate of change of heat energy. So we can track the power that we're putting into the ground as a function of time. If we go here, this is the outflow, and coming out here is a flow that's distributed over that surface and a temperature that's distributed over that surface. And neither the flow nor the temperature will be uniform. And so the the temperature times the flow times the density of water times the heat capacity, that ends up being the power per unit area. And so we take that and we integrate it over this outflow, and we end up with the power. So I made this one of these derived values, and we're going to integrate this expression here. This is the integrand. We'll integrate it over that surface, and we do that at each time step, and we can plot that up, and here's the result. This has units of power, or power, which is in this case watts. And so right at the beginning, when the temperature we put in is much different than the temperature in the ground, then we can shed quite a lot of power into the formation, 180 watts. But that changes really pretty quickly, and the amount of power that's going into the ground decreases. And here, after this amount of time, it's starting to flatten out. And let's see. Well, at any rate, this is going for, I think the total elapsed simulation time is 30 days. Okay, so I specified it. This is a little bit easier way of specifying the duration of the simulation. You can give units here, and so this is 30 days, but you notice that what it's doing is it's taking that specification for the runtime of 30 days, and it converts it into the internal units of seconds that it uses to do the calculations. And so then the display here is in units of seconds. And we could convert this back, but I think at this point the thing that I want you to see is that the power is changing by, I guess a factor of 2 here, really quite quickly, and then it levels out, and we're shedding over most of the time period in the neighborhood of 100 watts that is being put into the ground. And essentially it's 100 watts of power of heat energy or heat power that we're putting into the ground, and we could potentially also recover that heat later on. So this could be a way of storing energy that we recover later. One more thing that we have here that's interesting is to take a look at the temperatures along this profile. In this analysis, I assumed that the outer edge of this cylinder was insulated, so no heat is going to go across it, and also there's no flow. Actually, I mean there's no flow in this entire region except through the tube. And so if we take a look at the temperatures along this profile, are shown here. We see there's the second tube, so it's much cooler than the first. And then these are the profiles, and you can see they're done at many different times. But at the beginning, the temperature doesn't change it doesn't change out of the boundary. But towards the end of the simulation, it does. So we do have some interaction with the boundary, although it's pretty small. It's only a few degrees change out here at the edge. If we wanted a more accurate solution, something that would more accurately represent doing this in an infinite medium, then we would need to make this region a bit bigger so that it didn't interact with the boundary. But this is how you would go about checking. The other thing that is worth noting here is that if we, well, let's go, well, if we take a look at this, the cylinder here has it's no flow and it's insulated on the top and the bottom. Now, this is probably okay at the bottom, although we might want to make it a little bit deeper. But at the top, we would have the ground surface at some point. So what we're assuming is that this is really quite deep, so we're not interacting with the ground surface, and we're not having an effect there. And so somehow we're getting the water to go down the tube to reach this point without shedding any heat, so perhaps it's insulated. But if we were really to do a full simulation of this, we would probably want to include the ground surface and have the tube running down from the surface and look at the overall heat transport.